So we are going to go into this idea, properties of matter. So a property is just it's an attribute associated with something. Properties, we use them all the time, you know. And so, in fact, we're gonna go ahead and play 20 questions. I don't know if you're familiar with that. We have an Alexa at home. It's one of those things where you ask Alexa a question, or she plays music, or she keeps lists for you, and Alexa will play 20 questions. So we'll see how well they do with this. But properties can be, you know, what color something is, what something smells like, that's a property. If it blows up, that's a property. Or if it's capable of blowing up, that's a property. So here we go, 20 questions. Oh, I've got a few. I'm going to go ahead and connect it up to the internet. It's got a few videos I want to play too. Okay. Let's see if it'll let me do that. No? Yeah, there it goes. It's thinking. 20 questions, you might have played it like on your long trips and you have kids in the car and you're just trying to like get them to stop asking, are we there yet? So, oh, it's not going to let me do it. Well, I can see it, but you guys can't just because it's being dumb. So we're going to, the item we're going to think of is I decided on a hamburger patty. So I'm just going to tell you what it's asking me. Of course, the first question it always asks is our hamburger patty, which it doesn't know, that's what we're thinking of. Is it an animal, vegetable, mineral concept, or is it unknown? Hamburger patty, what do you think?
Animal.
Think it's animal? Okay, I think so. I know, it's like, okay. Is it fuzzy? Oh my gosh, I hope not. So that's a property. Is it fuzzy? No. If it is, don't eat it, right? Does it have 4 legs? Used to. This is pretty sad. Let's see. I think no. Okay. Is it water-based? Is our hamburger patty water-based? Probably quite a bit of water in it. I'm gonna say no, though. Okay, we're going with no. We'll see if it gets it. This is question number 5. Does it like sunshine? No. What? Right. I think we've thrown it off because we said it was an animal, so it thinks it's alive. Can it be used to start fires? That's an interesting question. Interesting property. No. If you're grilling it, I suppose. Is it crunchy? If it's burnt. Oh, okay, there's one that says sometimes. We're going to click sometimes. Could be crunchy. Can you see it in a zoo?
Yeah.
They sell them there. Oh no, I should have figured this out before I did this. What do you guys think? How many people think you can see it in a zoo? I think so. I'm gonna go with it. Okay. Oh no. Okay. Would you find it in an office?
Yeah.
No.
Sometimes, maybe.
Office.
I'm gonna say sometimes.
Most of the time not, though.
Yeah.
Okay, there's one that says rarely, so we'll go rarely.
Let's do rarely.
Okay, rarely. Okay. All right, rarely it is. Does it bring joy to people?
Yes.
Yes. It can.
I'm happy when I get a burger.
Okay. I'll say usually. How's that? Is it used by the police? The police? No, that's a clear no. Okay, I'm thinking no too. Well, this is a tough one. Oh, is it brown?
Yeah.
Yeah, now we're talking. Okay. Do you carry it in your pocket? No. The Hamburglar might. You know how he also had hamburgers all over the place. Is it a specific color?
No.
Hamburgers?
Yeah, no, it could be green sometimes.
It depends on how cooked it
I'm gonna say usually. That's true. That's true because it could be. Oh, that's true. It depends. I'll put depends because I agree. You're not supposed to eat your hamburgers rare anymore, though. So.
Really?
Is it usually warm?
I
Yeah.
would hope so.
Okay. Was it used over 100 years ago? What do you think, hamburger?
Yeah.
I'm sure it was.
Yeah. I don't know. We're gonna go with yes. Is it round?
Yeah.
Yeah. One dimension is.
A square.
Is it usually sliced or carved? Hamburgers are sliced or carved?
No, it's just a clump of minced meat and you put it in a ball. Unless they like have a machine that puts it out in like
Yeah.
a big tube and then cuts it.
Well,
up.
yeah, you can get that at Aldi, like the whole tube of brown, and I'm gonna say sometimes.
Little tube of meat.
Yep. I am guessing that it is beef, and this is one of its questions.
Dang.
I know. I'm gonna say right. That's its 19th question, and it said it won, so.
Okay.
Oh, goodness gracious. So,
How to go from asking like,
How to go from
is it
19
in an
to winning?
office? Yeah, to
Yeah.
You got like one and done.
So wait, what are the point of these questions again?
the point of those questions are, those are properties or characteristics. So when you play 20 questions, one person thinks of it, and the other person asks questions about it, so that's, that's it. Yeah, so properties. So switching gears back to your lecture slides. Okay. I don't know if you've ever heard of, oops, I need to pull this up. Like yin and yang. I don't know, I'm not, okay, yin and yang. They're kind of related, but they're, what's that?
Good and bad.
Good and bad. Okay.
They're balanced.
They're balanced. So they kind of go together. And I mention that because if it's going to go on to the next slide. There we go. No, it didn't. The next two slides kind of go together. They're properties, but they're related. And I'll try to kind of show you how they're related. I guess I need to close that out. And then we'll start again. Yes, that's your next slide, right? Okay. So we have intensive and extensive properties that kind of, they go together, good and bad. They're not good and bad, they're both good, I guess. But they're both can be used to describe matter. Now, intensive, I always remember independent. So intensive, remember independent. And independent of what? They're independent of amount. Okay, so these are properties that don't depend upon amount. There's a good list right here. These are all properties of matter, a way to describe matter. Something's color. So, for instance, there's a blue folder right there. We could say that that folder is blue if you have one of them. If you have 10 of them that were manufactured the similar way, same color, they're all blue. Okay, so blue doesn't care if I have 1 or 10. That's it. Okay. What temperature does ice melt at?
33. Well,
32 degrees Fahrenheit. Very good.
that's when it starts freezing, so I figured one more would be.
Yeah.
melting.
And it's like a tipping point. It could either freeze or it's weird. That's a good
Depends on
point.
if you're adding or subtracting energy from it.
Yep, it depends on what's going on around the water, exactly. But the temperature of ice to melt is about 32 degrees Fahrenheit or so. What's the melting point temperature of this table? You think it's higher or lower than 32?
higher.
I think it's higher, yeah, way higher. But that's a property of water, and it's a property of the material making up this table. And it doesn't depend on if I were to take a little piece of this table and melt it at that high temperature. Doesn't that sound kind of cool? I think we should. Or if I were to take the whole table, it would all melt at that temperature. Granted, if I have more table, I'm going to have more energy. Okay, but it's the same critical temperature. Okay, so those are independent of amount. So things that do depend upon amount then are extensive properties. So that's kind of the yin-yang. We have intensive, independent of amount. And we have extensive, it does depend on amount. So the IN in intensive, I always link up with IN and independent. So extensive depends upon amount. So I mentioned, for instance, this table. I said we were going to take a little bit of this table and we were going to melt it. Okay, or we were going to take a lot of the table and we were going to melt it. Okay, the amount of energy required to do that is extensive. It's an extensive property. The amount of energy that we need more energy to melt more. For example, the amount of heat given off in combustion. So, like if I were camping and I had identical logs, okay, and I was in one place going to burn 1 log, and another campfire I was going to burn 5 logs. Okay, if I could quantify the heat given off over the course of them all burning, the one with the 5 logs, I would get more heat from. Okay, so that's just kind of, so extensive properties do depend upon amount. We could go back to the folders. We could go 1 folder or 5 folders or 10 folders, and we could, those would be our 2 chunks of matter. We have 1 folder here, we have 10 folders here. Okay, a property of matter is how much it weighs. So of course, this one weighs more, okay? So mass is an extensive property. It does depend on amount. Then we have another couple that go together. We have physical properties and chemical properties. So in the 20 questions for the computer to guess that we were talking about a hamburger, it asked us various things, and a lot of these were physical properties. A physical property is one that you can gauge just by kind of looking at it, or you gauge with some sort of equipment, but you're not, no new substances are formed. You're not doing any sort of chemistry on it. So physical properties can be gauged without destroying the thing. That's it. So these are all examples of physical properties. Looking at it, of course, you don't have to do any sort of chemical reaction. A lot of times students, and we'll be talking more about the whole melting an ice cube and that sort of thing, the phase change from a solid to a liquid like that. Before you melt it, it's cute little H2O molecules, and once it's liquid, it's still H2O molecules. Okay, it didn't change in that sense. So that melting actually is a physical phenomenon, so the temperature at which something melts is a physical property. Whether something conducts electricity, how viscous something is. I don't know if you're familiar with this. What do you think? What's viscosity mean?
How thick it is.
How thick it is, exactly.
How you see it pours.
Exactly. That is a physical property. Yep. Okay. So looking at melting point temperatures, we have 2 white crystalline substances. One you take for your headache over there on the right, and the other one you put, naphthalene is used for mothballs, you know, so I would not eat naphthalene, okay? But they both have the property of being solid crystallines at room temperature, and they're white. So the deal is that the melting point temperature of aspirin is 135. The melting point temperature of naphthalene is significantly lower, 80 degrees Celsius. Those are both on the Celsius temperature scale. Now, we said that water freezes and melts about 32 degrees Fahrenheit. What temperature is that on the Celsius scale?
What's the formula for that again? Is it 5/9 or 9/5?
It depends on which direction you're going. But just focus on, a lot of times people have kind of committed to memory the freezing point temperature of water in the Celsius scale. It's,
Zero, isn't it?
yeah, thank you, it's 0. It's kind of a nice 0 Celsius. So 0 Celsius and 32 degrees Fahrenheit are the same. But yes, there's definitely a formula to go back and forth between the two. So what temperature on the Celsius scale does water boil at?
I think 100.
It is 100. Ding, ding, ding. So we got a kind of 0 for water to freeze and melt Celsius, and 100 for water to boil and condense Celsius. I mention that because then what we've done here is just put both of those white substances in boiling water. And so if it's boiling, then its temperature of the water bath is
100.
100, yep. So if it's 100, then of course you see that it is above the 80 required to melt the naphthalene, okay, but it's not to the 132 required to melt the aspirin. So just kind of a quick and dirty, you know which one to take for your headache, okay?
Just test this out real fast.
What's that?
Yeah, let me just test this out real fast.
That's right. Hold that thought. So when this naphthalene melts and all that, so if I were to take this naphthalene tube out, test tube out, what would it do if I took it back out to normal temperatures?
Probably re-solidify.
It would re-solidify, exactly. So the cool thing about melting, you go back and forth and you get the same stuff back. Okay, so no new substances are formed. So this is just to kind of show you that color is a nice way to, if you're playing the I'm thinking of game, it's a property, it's a physical property. Viscosity. Now I kind of had some, I wonder if this will work. I've had some, this semester, some issues with the computer, but let's see if this will work. Ooh. Okay, so this one, I don't know if you guys can see it. Can you guys see it? It's a couple of beakers. It's talking about viscosity. What about that one? Okay, so now it's,
More hisses.
yeah, much more viscous. Exactly. Looks like Caro syrup. I think it's glycerin was what the caption said. So just kind of quick and dirty, you can, again, without any sort of chemistry, taking it to the lab and analyzing it, breaking it down, forming new compounds, you know what it is, which one to put on your pancakes. Okay. See, last time I did this, then I had to go. Okay, cool. That your next slide? Okay, so physical properties, no new substances are formed. We'll be talking about chemical reactions, obviously, after we kind of talk about matter and elements and compounds. We'll talk about chemical reactions. And in a chemical reaction, new substances are formed by definition, chemical reaction. And we're going to talk a little more about that. But the thing about a chemical property is it destroys the sample. Bottom line. To measure it, you have to destroy the sample. Bless you. I worked in an environmental lab capacity for a couple different places, and oftentimes we would send samples away for analysis, and sometimes you wanted like a whole list of analysis. So of course the lab that's doing the work would do the physical properties or characteristics first, and then they would do the chemical properties because they have to destroy the sample in doing that. So the sample is destroyed, new substances are formed. Be can read my writing. That's new substances are formed. So chemical property, examples of chemical properties would be these down here. You know, if the stuff reacts with water, and I have a video to kind of show you about actually sodium reacting with water. Something that, for instance, we talked about burning, what were we going to burn? Logs. The fact that a log will burn and the way that it burns is actually a chemical property of the log. So let's see if this one plays. Do this. Wish my sound worked. Okay, so this is sodium metal. I don't know if you guys can see it. So we used to have sodium metal, but it's been, when they lab packed out the stock room, that was one of the things that they took. And it was always has to be stored under kerosene. So you're like, oh my gosh, store that under kerosene. But you don't want any sort of water molecules to get to it, so. Okay. Sometimes I'll tell you right away that it's hard to know if something dissolved or if something really chemically reacted. I'm just going to kind of describe what this would do. This, let's see, what's the symbol for phosphorus? It's one letter. It is P. P for phosphorus, exactly. Phosphorus, actually, we talked about diatomic elements, I think, the other day, didn't we? Phosphorus is one that wants to be a quartet. So actually P4 is probably how you're going to find most phosphorus, buddied up with 3 other phosphorus atoms. Phosphorus does not like air. It reacts violently with air. So one of the things, if you Google phosphorus reacting, is you can take paper and you can coat it with phosphorus. Okay, of course you need to store that paper away from air, and you can take that paper out and it will just go into flames when it reacts with.
That'd be cool. Can we do that in the lab?
No. I'm not sure this is true, but I heard that MacGyver, I don't know if you're familiar with, that he used that to his benefit before. No, we cannot do that in lab. So do you guys have these to fill in as we go?
Yeah.
Okay, awesome. So chemical, let's say physical or chemical. So we're going to see a show of hands. How many people think color is a physical property? Okay, we're looking like we're unanimous there. Yes, it is a physical property. On your unit exam, I will actually have a section on your first unit exam to ask you questions like this. So, iron is transformed, sounds like it's changing into rust. How many people think that's physical? How many people think that's chemical? I do too. Very good. Let's see, dynamite can explode. Physical? Chemical? I'm liking chemical. Yep. We'll talk more about density, but density is how kind of compact matter is or how fluffy something is. So the density of uranium. So do you have to do any sort of chemistry to measure its density? Nope. Just get its mass and its volume. So it's physical property. The temperature at which something melts, we said, was a physical. Yep, physical property. And color, again, would be physical property. Yep. Very good. Okay.
So chemical properties are just a reaction with water and combustibility, right?
Well, those are examples of chemical properties, but anything where you have to do some sort of chemical reaction to assess its property, yes. So there could be other ones. But yeah, you got it. That's it. So these will give you some exposure at doing that sort of problems. These will be due on Friday. And I will go ahead and take screenshots and email these too. Any questions? No? Cool. Okay, so this is something that we've been talking about. Matter, all matter is made up of atoms, and it kind of branches out when you go to classify it. It can be a pure substance or it can be a mixture. And if it's a pure substance, bless you, it can either be an element or a compound. And if it's mixture, it can be homogeneous or heterogeneous. So this concept, physical change and chemical change, bless you, totally goes along with what we were already just been talking about. To measure a physical property, no new substances are formed. When a physical change occurs with matter, no new substances are formed. It's the same substance, but just in a different form. So sometimes I get to I'm like, that's like deja vu. So physical change goes along with physical property. So examples of physical changes where no new substances are formed would be changing its phases. If you just grind something, and did we talk in here about blending up the pizza to make a homogeneous mixture? Okay. Honestly, that's an example of a physical change you should be able to distill out at the molecular level. Can you imagine that? Dissolving sometimes is an example of a physical change. If you take water and you add some salt to it, okay, you could actually get back you guys told me I could evaporate the water back and I get the salt back, okay? But now the little video I showed you with the sodium metal, okay, in that case, if you evaporate off the water, you're not going to get back your sodium. Okay, so.
Why is that again?
Because your sodium has reacted with water to form a new substance. So here is water in its three physical phases, kind of from left to right. The left is the ice, and so I think you guys told me that it has the most intermolecular bonds, okay? And but does it move? Does it move at all when it's ice?
Vibrates.
What's that?
Vibrates.
It vibrates, yeah. Yeah. All matter is moving. All matter is in motion. And if it's stuck together, yeah, it vibrates, but it can't rotate easily or relocate. Okay, so liquid then is got less bonds, a little more activity, and a gas has no bonds, all sorts of activity, all sorts of energy. Yep. And we did this one before, didn't we? This little matrix thing. Okay, so from solid, liquid, gas. I'll let you kind of fill that in. Every once in a while now, my tests, my unit exams, I give you back your graded exam for you to keep, which is cool. And so every year I kind of change it up a little bit, but some years I kind of ask information about this. The three phases of matter and how are the phases of matter with regard to intermolecular bonds and kinetic energy. And will that substance take on the shape of its container, or is it stuck with its shape? Will that substance take on a new volume, or is its volume set? One of my deja vu slides. So probably most important for the next few slides are these two aspects of matter in the three phases. So matter as a solid has the most degree of intermolecular bonds. and it has the least amount of kinetic energy. And all the way extreme, as a gas, it has no intermolecular bonds, and it has a lot of kinetic energy. So those intermolecular bonds are actually the things that are going to be broken or formed as you change phases from a solid to a liquid or a liquid to a gas. Those intermolecular bonds, not the chemical bonds. So, for instance, if I draw a little water molecule here, H2O, and I draw another one up here. Is this what I drew on the board over there the other day? Okay. And in red, I'm going to put my intermolecular bonds. So here we go. Connect this up to that's my intermolecular bonds. So when I heat up, if this is a solid, when I heat it up, I'm going to break those intermolecular bonds, or at least some of them, and it's going to form a liquid. So here are the three physical phases, solid, liquid, and gas. As you go from left to right, you are breaking bonds. But I'm hoping you guys are good with this. We're breaking intermolecular bonds, the ones that in red on the previous slide. Intermolecular. The opposite of intermolecular, or in contrast to intermolecular, would be the chemical bonds. So in other words, the little water molecules, these right here are not being broken. Those are steadfast. So we break bonds from left to right, and as we go from right back to left again, as a gas goes to a liquid, what do we call that? What do you think? Con what? You got the first part right, I think. Condensation, condensing, yep. And if something goes from a liquid to a solid, we call that? Freezing, yep. Okay, so in those cases, it's cooling down and bonds are being formed. Yep. So from left to right, okay, in order to melt ice or to take liquid water and evaporate it, you need to add energy, requires energy. And as it goes from a gas to a liquid or a liquid to a solid, bonds are being formed, and this is a little bit less intuitive. That actually will be pushing out energy. In meteorology, we talk a lot about, see if you guys know what this is. Yeah, it's a cloud. Thank you. Whew. Thanks. So in a cloud, it actually has the little cloud particles are either ice or we'll just say they're liquid. Little cloud particles are liquid. So if it goes from clear skies to you look up and then actually you see the formation of a cloud, it's actually gone from, there was water vapor, like if it's humid, okay, water vapor, and it's actually gone to a liquid. One of the things then happening in that vicinity is it is actually liberating a lot of thermal energy. So if you have like a little thermometer up there in the vicinity of the condensation to form that white milky cloud, it's warm. You guys hear that Hawaii's going to be hit by hurricane 1 or 2? President Obama's going to go, and I know it's a conspiracy. But yeah, the whole hurricane thing has a lot of clouds, and what actually drives the energy of a hurricane is just this, what we call latent heat of condensation. We'll be talking more about that, how energy is released during condensation. Okay, so it takes energy to break those bonds, kind of from left to right. And remember, bonds, we're talking about no chemical bonds. We're always talking about intermolecular bonds. And then when bonds are formed, we may not always see it, but energy is released. So just to make sure we're all on the same page, what do you call when a solid goes to a liquid. Melting, exactly. For whatever reason in physical science, they also call that fusion. I do not know why. I've never known why. We won't, but you might run into that. Okay, so what if something goes from a liquid to gas? We said that's, no, that's gas to a liquid, so I tricked you. We didn't do this one yet. Liquid to a gas is evaporation. Yep, you got it. Evaporation or vaporization, same thing. So a liquid to a solid we said was freezing. Yep. And then a gas to a liquid is
Condensation.
condensation. Very good. So we're all kind of on the same page. I think the most fun comes when matter transitions, but it skips its liquid state. Okay. Oops, I'm not going to show you this. My videos aren't working. There's a figure from your textbook about evaporation. Is this not cool or what? So, of course, this is the heat we're applying. Does water evaporate even if you don't have a flame? Because, yeah, it does. That is so cool. It's kind of a random sort of thing. Basically, what happens is that some of the liquid particles get enough kinetic energy to basically break away from their bodies. Okay, and they turn into vapor. So what I started to say, I think the fun begins when it goes back and forth between a solid and a gas, but it skips the liquid phase. It happens all the time. It's like, for instance, when frost forms, okay, think of, we're going into fall here, okay? So one of these days you're going to get your frost warnings. So it's going to be maybe, I don't know, it has to be below 32, right? Might be 30 or something like that, 29. And it will go straight from being a vapor to being frost, a solid on your little, this is my leaf, my little grass leaf. Isn't that cool? That's called deposition. Deposition goes from a gas to a solid, like frost. Gas to a solid. Here's one for you. How many people in here have have use ice cube trays instead of, anybody in here like ice cube trays in the freezer to make ice? You have a, what's that?
I have one in my mini fridge, but I don't use it.
Okay. Well, if you did use it, the problem is, especially with mini fridge sometimes, is you don't revisit it very often. So you fill up your tray with water and then you'll come back maybe 2 weeks later, and there won't be any ice. I don't know if that. But what happens is
Where it just gets lower and lower.
it gets lower and lower. That's exactly what I'm talking about. And what happens is it froze. I don't know, a couple hours, 2-3 hours. It froze. But then what happens is that ice, that solid water, actually sublimes into your freezer, and it coats your freezer. It coats your hamburger. Gives you a frost burn. Okay. Mm-hmm. It is annoying. So I kind of use the word sublimation for that. I think I'm going to show you a video and then we'll call it a day. I hope this works for you. What element is the symbol I? Iodine, very good. An iodine is part of Hoffernickel, right? So it's always going to be what? I2? Come on.
Why do people put that in their water? Iodine.
Yeah. Yeah, I think I have heard that. Oops, I guess I want to go like this. Yeah? Yeah, you can use it to treat open cuts. Okay, hopefully you guys can see this. The title is sublimation of iodine. Okay, so those little pellets there are the I2. Okay, those are the iodine. And it has a very low point at which it will break the intermolecular bonds. So here we go. They're heating it up, and that gas there, it skipped the liquid stage. Basically, they applied heat, and it went right from being a solid to being a gas. Is that not cool or what?
Interesting color.
It is. And then this thing at the top, all it is a flask with ice in it. It's like a cold finger, sometimes they call it. And so actually where the glass is, you see that gas then re-solidifying. It skips the liquid phase again too. That would be what? Deposition.
So, what's the temperature for it? Does it turn into a liquid?
Nope, it skips the liquid. It skips the liquid under normal pressures. Now, if you monkey with the pressure, you might get your liquid phase back again. Yep, yep. Isn't that cool? Okay, that's all I have today. We'll see you tomorrow in lab.